Hello everybody, welcome again to the lecture of downstream processing in biotechnology. This lecture is the last section of the adsorption. Okay. Previously we talked about the principle of the fixed bed adsorption. Now lecture I given you an example to calculation based on the fixed bed adsorption. The first example, right, we will adsorb the lactate dehydrogenase. This is the enzyme. This enzyme is being adsorbed in a fixed bed with 1.3 meters long. That's right. The pad with modified cellulose. The adsorbent is cellulose. The bed is 7 centimeters in diameter. That's right. The white fraction of the column is 0.3, and a dilute feed containing 1.7 milligram per liter of enzyme is being fed to the bed. At this dilution, the enzyme is adsorbed according to the linear isotherm. For this case, we assume the isotherm, the relationship between the amount of solute adsorbed on the silicate sulfate equilibrium with the amount of solute in the liquid solution. Is expressed by this relationship. Okay. For this case, the velocity in the base produce breakthrough at 6.4 hours. This is the TB. That's right. We know TB is 6.4 hours. And the bed is expired in 10 hours. This is the TE. That's right. This means all of the solute from the feed equal to the outlet. That's right. Okay. The question is determine the length of the adsorption zone at the breakpoint and the length of the equilibrium zone at the breakpoint or breakthrough. That's right. And the last one, the fraction of bed capacity which is being used for adsorption. Okay, the first one, calculate the adsorption zone or absorption length. The adsorption zone is take place between TE and TB. Right? TE minus TB. We know TE 10, TB is 6.4. Okay. Delta T or TB, TE minus TB equal to 3.6. We'll have the bed, leave the bed. The length of the adsorption zone is L multiplied delta T divided by TB. That's right. L multiplied delta T divided by TB. Delta T is 3.6, TB is 6.4. That's right. Length of the column is 1.3 meter. That's right. The length. That's right. Okay. The adsorption zone, the length of the adsorption zone is 0.73 meter. This is the first question. And the second question, calculate the equilibrium zone at the breakthrough. Equilibrium zone at the breakthrough. Right. Equilibrium zone at the breakthrough is the remaining zone. So we talked to you already that we have two zones, right? In the curve, I will show you in the curve. This curve, we calculate the adsorption zone already, and the remaining zone is equilibrium zone. That means L minus adsorption zone, we get equilibrium zone. We know the adsorption zone already from the first question, 0.73. The length of the column of the column is 1.t. 1.t minus 0.73. That's right. And then you get the 0.57 meter. This is the equilibrium zone. Equilibrium zone means the zone that adsorbent is already saturated with adsorbent. There is no factor to adsorbent for this zone, for adsorption for this zone. And the last one, the fraction of bed capacity. The fraction of bed capacity, we can calculate delta equal to 1 minus delta T divided by 2 TB. You know delta T, you know TB, you can calculate the fraction is 72% of the adsorption. Okay, for this example. Okay, the second example, cephalosporin adsorption. For this case, we will adsorb antibiotic of cephalosporin. That's like cephalosporin. Using the adsorption with the resin, with the ionic resin, with the weakly ionic resin. We use the resin to absorb the antibiotic. And also, for this case, we know the isotherm or equilibrium relation. So at Q equal to 32, right, multiplied by C power 1 over 3. That's right. The unit of Q, you know, is the milligram of solute per volume of adsorbent. For this case, it's the resin. C is the gram or mass or mole of solute per volume of solution. Okay. For this case, we now want to measure adsorption in fixed bed. The bed width we should is 1 meter long. The length of the height is 1 meter. The diameter of column is 3 centimeter in diameter. And the bed density is 0.67 cubic centimeter resin per cubic centimeter of the bed. Our fit solution contains 4.3 gram of antibiotic per liter of the solution. When we use a superficial bed velocity equal to 2 meters per hour, we obtain the breakthrough as shown in this figure. This is breakthrough curve for this example. Okay. The first question, determine how much of the feed is lost if we stop the adsorption when C equal to 0.4 gram per liter. If we stop the adsorption when the outlet concentration of the effluent concentration is equal to 0.4. How long? And the second one, estimate what fraction of the bed capacity is used at the breakthrough from question A. Okay, we assume C equal to 4 gram per liter. This is the TE, at temperature, time. Okay, the last question, estimate the rate constant for the bed. Okay. From the graph, this graph shows Y is mean C, gram per liter, and time. We plot concentration with time for this case. For this case, we can calculate the fraction loss. Fraction loss is calculated from the area under curve of C versus T from the start to the breakthrough. The breakthrough for this case is we talk about 0.4. We stop at 0.4. Okay, we 0.4 concentration. This 0.4 concentration. 0.4 concentration, and then you drag in the horizontal to intercept with the breakthrough. That you can drag this, you get about 6.t. That's right. This 6.t. This t for breakthrough. This can, okay, you can integrate from 0 to 6.t. This curve, you get the area under the curve. That's right. Area under the curve of this, and then you divide this by the CF multiplied by TB. 6.t, you get 0.02, which is the fraction loss. And also the fraction B. Fraction B is estimated fraction of the bed capacity. The bed capacity. For this case, you can use the equation that's the same previous example. 1 minus delta T divided by 2 TB. Delta T for this case, the x hat time at C equal to 4. You have to calculate what is the TE at 4.0 gram per liter from the curve. That's 4. That's right. It's approximately 9 hours. This is the TE. It's 9 hours. You get TE is 9 hours minus previous time is 6.3 divided by 2 multiplied 6.3. You get about 79. That's 79%. That's the adsorption or the column used for adsorption. That's right. Used for adsorption. Okay, it's about 21% is unadsorption. So, and the last question, you calculate the rate constant of the bed. The rate constant of the bed. Okay. From this, we plot the operating line and equilibrium line. The equilibrium line plot this. Q equal to 32 C power 1 over 3. That's right. This is you plot between Q and C. That's right. This is C minus C star. Sorry, this is C minus C star. This is also C. That's right. You plot Q and C. This is the equilibrium line. This and our operating line. Operating line is linear relationship. This is the operating line. If you try this C equal to WQ. That's right. It's equal to WQ. S is the amount of feed. W is the amount of adsorbent. That's right. Volume adsorbent. Okay. You plot Q with respect to C, right? Q versus C. You get it, and then this is the feed. You start from 4. That's right. You start from 4. This case, 4 gram per liter. That's right. Or 4,000 ppm. For this case, 4,000 ppm. Okay. You start from this. Okay. You start drag. This is the C. That's right. C, and then you drag in the vertical line. It is C star. That's right. And also you get C star. Get C star, something like this. It's maybe up to you can draw like this. You can draw like this. That's right. Or you can this is C and C star. That's right. This is C, this is star, this is C, this is star, this C, this is star. You get C and C star for many terms. That's right. Many term, many pair for the set. And then you plot for this pair C and C star. You calculate 1 over C minus C star and versus C. You get 1 point. And also in this point, you get another point. 1, 2, 3, 4, something you can write this C and C star from this. That I get 1 point, 2, 3, 4, 5, 6, 7, 8, 8 point already. You get 8 point, you get some like this. Right. And then 0 like this. This you obtain from this. And then we start from C, F. That's right. This is the final, it's the C. C is 0.4. That's right, 0.4. Or 400 ppm. That's right. And then you calculate the area under the curve. Area under the curve, like this. You calculate the length or the height of the column. That's right, height of the column. You know epsilon, you know U. You can evaluate Ka because you know L already. You know L, you know epsilon, you know U. And you can use the integration previous graph for this term from C to CF. You substitute this, substitute this, substitute this, substitute the area under the curve. That's right. Epsilon is 0.33. U is 2 meters per hour. The area under the curve is 31 divided by Ka. You know L, 1 meter. And then you can solve for Ka. That's the mass transfer constant K multiplied by A equal to 20 per hour for this example. Okay. Okay, for the next, that's why we talk about the capacity of the column and the scale up. This is the last section for the adsorption. Mostly the scale up is based on the information from breakthrough curve like this. We will use this curve or breakthrough curve to explain the lab scale and scale up to the pilot scale or plant scale. That's right. This is done by the assumption that when the length of the column is changed, the solute velocity or solution velocity and the length of the unused bed is constant. For this case, we determine or the scale up based on constant solute velocity and the length of unused bed. That's right, unused bed. Okay, for this case, the shed area is the bed capacity that the adsorbent can absorb. Adsorbent can absorb this area. The left hand side, this area is the bed of adsorption. This is the bed of unused bed. That's right. This is adsorbed already. This is unadsorbed. That's right. Okay, this is the true area. Okay. Amount of the adsorbed bed that adsorb until reach the breakthrough curve. Amount of adsorbed bed until you calculate at TB. Mostly we calculate at about 0.05 cf or 5% of cf. Is TB of breakthrough. As it TU equal to integrate 0 to TB of 1 minus C over CF dt. 1 over CF dt of this curve. If you plot between 1 minus C over CF dt. That's right. Okay. This is equal to integrate dt, that's right. minus indicate C over CF dt. Okay, indicate dt, we get T. Indicate C over CF dt, you can calculate from the curve like this, from the under the curve. Okay, the area under the curve. Okay, and then the total capacity. The total capacity you have to indicate from T0 until final time. That's right, at T0 to final time. Okay, we indicate T total equal to 0 to infinity or infinity of the final time. That's right, dt. Okay, if we represent ST the total base length, the length of the column, SB the length of the base that used for adsorption until reach the base 2. The length of the base from the time 0 to time B is SB. And SU and B is the length of the height of the column that unused for the adsorption, equal to ST minus SB. Okay, if we consider the ratio of SB and ST, is TU divided by TT. TU or TB, that's right, TT is total time. And therefore, SUNB divided by ST equal to 1 minus TU divided by TT. Okay, we can use this relation to calculate the scale. For example, that's right, SUNB is the same for the lab scale and pilot scale or plant scale. That's right. It's the same. That means the same SB, TB. SB lab scale divided by TB lab scale, but equal to SB pilot scale or plant scale equal to TB at pilot scale or plant scale. That's right. Okay. And then you can calculate the height of the new column. ST new equal to SB plus SUNB, something like this. Okay. The method can be scaled up. This is based on the derivative system, but no change in mass velocity. That's right. For this case, assumption is the velocity u is constant, and usage base height is constant. It's true. That's right. Assumption. Okay, we will consider like this example. For this case, we will adsorb the pharmaceutical compound. That's right. In laboratory scale column with diameter is 5 centimeter diameter and 15 centimeter in the height of the column. The feed flow rate is 400 units per hour, and the feed concentration is 0.75 unit of activity per liter of pharmaceutical product. It is designed to scale up the process to operate in a column with 30 centimeter in height. The lab scale is 15, but the scale up is 30 centimeter in height. The question is what breakpoint time can be expected in 30 centimeter height. Okay, and from the lab scale, we know the concentration, that's right, effluent concentration as a function of time, like this. The time is less than 20.5, small concentration is approach 0. That is the complete adsorption. That's right, complete adsorption. Okay, and then you can plot between C over CF and T. That's right, C over CF and T. And then the base capacity at breakpoint. Mostly at the breakpoint, we use C equal to 0.05 CF, 5% of CF. And then from this relation, that's right, for the 5%, this is 0.1. This is 0.05. To drag at 0.05 CF, we did C over CF. Okay, we get TB is around 21 hours. That's right. This TB is around 21.5 hours. And then you can calculate TU. TU is integrated from 0 to 21.5 1 minute CF divided by CF dt. This is approximately indicate dt minus indicate C over CF dt. That's right. Indicate over CF dt. This term, that's right. For this term indicate dt, you get T, that's right, T 21.5 minus 0, that's right. And also from indicate C over CF dt, alien the curve like this, using this, right, you get about 0.4, 0.3, something like this. You get the result is 21.2. That's 21.2. Okay. This is the TB or TU. That's right. This is TB or TU is the same. Okay. And the second one, the total bed capacity at point CF divided by CC divided by CF equal to 1. That's right. At 10% or approximately 100%. That's right. Is it about 1? That's right. You get this is TE. That's right. You can approximate is 95%. 95%, or for this case we use 100%. Is not worry. Don't worry. It's okay for 100%. Okay, for 100%, you estimate time at this point. That's right. It's when 44 hours, and also you indicate TT from 0 to 44 hours, and also the same. You get DT minus C over CF DT. That's right. 0 to 44. You get about 31. That's right. Okay, the first step indicate you get this, same this, and also this area under the curve from this area under the curve from this. Okay, this is approximately 31.5 hours. That's right. From the indication. That's right, from the indication. This means it, for this case, you get 44 minus this term. That's right, minus this term. Okay, you get 31.5 hours, and then you calculate SUNB, unused height. That's unused length equal to ST1 minus TU over TT. ST is 15 centimeter. TU is this. That's right. TT is this. You get 4.9 centimeter. Please remember that for scale up with this model, that's right, we assume the unused bed height is constant. Okay, for this case, you calculate SB. SB equal to S total divided minus SNUB equal to 10 plus 1. And then you use the relationship between this to scale up. This to scale up. Okay. For this case, the SB for 30 is 30 centimeter minus SNUT. This is the same for scale up. 25.1. This is NB30. Okay. For this relation, SB15 divided by TB15 equal to SB30 divided by TB30. 15 is the 15 centimeter in the height and 30 centimeter in the height. And then you can calculate TB, T breakthrough for the larger column. That's right, larger column with equal to 53.43. That's right. If you scale up, if you increase the height of the column, the time to the breakthrough is also increased, because for this the time breakthrough is about 21.2. And this scale up from 15 to 30, time for breakthrough is increased to be 33.40. Okay. We talk to you about the adsorption. This is the last lecture for adsorption. We talk about 4 or 5 lectures. Mostly the adsorption, we talk about the bad adsorption, continuous adsorption into the tank, and frequent adsorption. This is the most common used in the adsorption. And also we talk about isotherm. Isotherm, we talk about the equilibrium concentration, the relation between solute concentration in solution and solute concentration on the surface of solvent. It is very important. The mostly, if we utilize the design equation, we need at least 2 equations: equilibrium relation and mass balance equation. That's right, equilibrium mass balance equation. Okay, I say thanks for you that you are interested in this lecture. Okay, you stop for this lecture. Thank you.